Hey everyone, welcome to Chemistry 1111. This is a screencast with your friend and mine, Dr. C. We're looking at WU9 Lecture 2. So Lecture 2 in Unit 9, which is the last chapter that we do in Chem 1111. And this is an interesting topic, quite practical, called colligative properties. The G is hard, so it's not colligative, it's colligative properties. And the thing about colligative properties is you care about the amount of particles in the solution, not the identity so much as the amount, how much we have. And this is going to help us understand vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. So, if you're looking in your textbook, we're on page 429, and I'm just going to make some notes and do some sample problems with you here. So you can alter the properties of a liquid by dumping in a solid. If you add salt to water, then the water will boil at a higher temperature. So if you're making Kraft dinner, which I'm going to have for lunch today, the cooking will happen at a higher temperature. It'll also taste better because the more the salt there is, the better it tastes. If you add antifreeze, ethylene glycol, to water in an automobile radiator, that freezing point will be lowered than zero, so you won't get the water freezing at zero, which will cause all sorts of problems with your car. So the ones again that we'll look at are vapor pressure, freezing point, boiling point, and osmotic pressure. And we'll start by looking at the vapor pressure reduction and how that works. So I'm going to scroll down here, and I see a dynamic equilibrium on the left, which involves a solvent and a solute. Let's say it's water, because that certainly looks like water, doesn't it? So on the left-hand side, we have liquid water, and above it, we have water vapor, and there's a dynamic equilibrium between them. Remember that we have to have the system has to be closed, right? We have to have it all nice and closed system so it doesn't escape. And every now and then the water vapor molecules lose energy and they fall back down to the surface and even into the bulk of the liquid water while the liquid water comes out. Now, on the right, we have put in some solute, and so now the water is not leaving as easily. There's a few ways to think of this. One is that some of these solute molecules are blocking exit paths for the water to escape from the liquid to the vapor phase. Other explanations are that the solute attracts water molecules towards it that would have otherwise tried to get out of the solution. So a few explanations. We're going to focus more on the results and the math behind it. But the vapor pressure of a solution is always lower than the vapor pressure of the pure solvent. Okay? And you can watch some animations about that if you want. So the math goes with Raoult's law. I used to think it was Raoult's law, but no, it's Raoult is how you pronounce it. But I'll always end up calling it Raoult's law. So in a solution, the vapor pressure of the solution equals the mole fraction of the solvent times the vapor pressure of the solvent. Okay, so the vapor pressure of the solution is going to be less than the vapor pressure of the pure solvent, and it's going to equal the mole fraction of AXA times PVAP of A. You could also write it as the vapor pressure of the solution equals 1 minus XB times the PVAP of A, right? Assuming there's only one solute dissolved in one solvent, okay? So, right, then the XA plus XB would equal 1. So then 1 minus xb would equal xa. So that's sometimes a convenient way to write it. And the change in vapor pressure, the vapor pressure lowering, would be well, the absolute value of the vapor solution minus the pure vapor pressure. If you want to have it always a positive value, then you would take the vapor pressure of A minus the vapor pressure of the solution. Vapor pressure of pure A minus the vapor pressure of the solution. Okay, so that shows the vapor pressure lowering. So let's try an example here. I got my calculator. Calculate the vapor pressure of a 5% by mass benzoic acid solution in ethanol at 35 degrees Celsius, and they tell you the vapor pressure of pure ethanol is 13.4 kilopascals. Okay, so water is not always a solvent we use. Here we're taking an organic acid called benzoic acid, and the molar mass is, I'm going to look right there, 122.1 grams per mole. And ethanol's molar mass is 46 grams per mole. Right, get those molar masses right away. Whenever there's mole fractions, just go ahead, get the molar masses. Maybe you won't use all of them all the time, but you might. So 5% by mass. Okay, so let's get the mole fractions of everything. So benzoic acid, I don't know how much I have, but I know it's 5%, so let's use 100. So I'll have, in 100 grams of the solution, I'll have 5 grams of benzoic acid, right? 5% by mass. So 5 out of 100, 5% times 100 is 5. And the ethanol, if the total mass of the solution is 100 grams, then the ethanol is 100 minus 5, which is 95 grams. Then I can get the mole fraction of the benzoic acid, 5 grams over 122.1 grams per mole, which is 0.041 moles. And of the ethanol would be 95 over 46, which is 2.07. Total number of moles would be, I want to do that, and total would be 2.07 plus 0.041. I'm going to take my calculator here. 2.07 plus 0.041 is 2.111 moles. Okay, so then the mole fraction of the ethanol, the solvent, would be 2.07 over the total 0.981, and the mole fraction of benzoic acid, of the solute, if you were asked that, would just be 0.041 divided by 2.111, 0.019. You got to be a bit careful with decimals here, or you may lose the effect altogether. Or rounding off might magnify differences too much. So, what was the question? The vapor pressure. Well, it better be less than 13.5. So, here it is. The vapor pressure of the solution is the mole fraction of ethanol, 0.981 times 13.4. So 13.14. So it is. It was lowered by 0.26 kilopascal. Okay. Shall we try this one? Why not? Okay. And I'm going to look at the practice exercise answers, which are usually what? At the end of the chapter or at the end of the book? I always forget that one. Practice exercise answers. Okay, this is 9.6, and it says that it's reduced by 0.296 kilopascals. 0.296 kilopascals. Okay. Well, let's see if that's the answer. How much is the vapor pressure reduced below 101.3 kilopascals by dissolving 12.5 grams of sucrose? Okay, I'm going to do the margins here. 12.5 sucrose. Well, let's see. I want to say that's 342, but let me do it. 12 times 12 plus 22 plus 11 times 16, 342. Now I'm impressed with that, eh? That I knew off by heart what the molar mass of sucrose is. I'm reading an interesting article right now in the New Yorker magazine about sucrose treated with silica to increase the taste bud reception of the sucrose molecule, so you won't eat as much sugar to get that lovely feeling of lots of sugar. Anyways, 12.5 divided by 342 is 0.036 moles. Okay, so we've got 0.036 moles of sucrose. We've got 225 grams of coffee. Assume coffee has the same vapor pressure as pure water. Okay, that's great. Well, I would need a bit more information to do that, right? I need to get the molar mass of coffee. So let's have some fun with this. Let's get the molar mass of coffee, and then we can get the moles of coffee. Then we can get the mole fraction of both, and we can also get the vapor pressure of water at 100 degrees Celsius. Okay, so I'm going to go on to the interweb. That's always a scary thing, isn't it? Let's get molar mass of coffee. Maybe that's written somewhere. Molar mass coffee 194.19. Okay, I'm going to write that on a piece of paper here. 194.19. And let's also get the vapor pressure of water. It's 373 Celsius in kilopascals. Vapor pressure of water at, well, it's 100 Celsius in in atmospheres. Well, surprise, surprise, it's 760 millimeters of mercury. Okay, that's good. And then how many kilopascals is that? So, well, that's 1 atmosphere to kilopascals. There it is. 1 atmosphere to kilopascals. 1 atmosphere, 101.325. Okay. 101.325. So there, I did a bit of gas law stuff. Some of you could have done that quicker than me, and good for you. Okay, so let's see. We got the 12.5 grams of sucrose, 225 grams of coffee. So the coffee, I'm going to take 225 grams divided by the molar mass of coffee, which I just wrote down, 194.19. 225 divided by 194.19, and I get 1.159 moles of coffee. So the total number of moles, I'm just going to add together that plus the sucrose, 0.036, and I get 1.195 moles all together. Okay, so the mole fraction of coffee, which is my solvent, is going to be 1.159 divided by 1.195, 0.970. Okay, so the vapor pressure of the solution is the mole fraction of the solvent, 0.97 times the vapor pressure of the pure coffee at 373, which was 101.3 kilopascals. They actually tell you that in the question, don't they? So 0.97 times 101.3 is 98.2 kilopascals. Okay, so we then have the vapor pressure is reduced below 101.3. It's now 98.2. So it's 98.2 minus 101.3, and you get 3 kilopascals. So why does it say 2.96? Let's start using a different value for coffee here. Let's think for a second here. Grams to moles divided by the molar mass. Molar mass of coffee is 194.19. 225. Let's get the sucrose right. 12.5 divided by 342.036. Good. 225 divided by 194.19 is 1.159. Okay, so that's the moles. 1.195. So the mole fraction of coffee is 1.159 moles over the total. 1.159 divided by 1.195. 0.97 times 101.3 is 98.2. Okay, my only guess why that answer isn't coinciding is that people are using different values for molar mass of coffee, but the this process is the same. Is molar mass of coffee always the same? Okay, well, caffeine's 194.19, but we don't know what the other ingredients may be in there. So I'm not going to fret about that. We got the right process. We've done the math correctly. And yeah, now it could be shifted by a factor of 10, and the answer key is 2.96 is almost 3. So let's try this one together in class just to double check it. Okay, so let's keep going here. Now, the equations that we just looked at, Raoult's law, works if the solute itself doesn't have a significant vapor pressure, right? Sugar doesn't have much of a vapor pressure. You don't smell a bunch of sugar vapor above solid sugar. In cases where both the solvent and solutes are volatile, like benzene and toluene, those are petroleum distillates, those will have a smell like gasoline. The total vapor pressure above the solution is the sum of the contributions from both the solvent and the solute. So both have a role in that. And the solvent in this case is just they're both liquids, so it's the one in greater volume can be denoted as the solvent, and that is a solute. As you do more of this physical chemistry stuff, you'll end up not calling them solutes and solvents. You'll call them components. So you have component A and component B, and you'll have a 2-component system and then a 3-component system. Get into all these phase diagrams, all this fun stuff. So we see here that for the solution, the vapor pressure of the solution is the mole fraction of A times its pure vapor pressure at a given temperature plus the mole fraction of B times its pure vapor pressure at a given temperature. So let's look at a diagram, a graph that you should be able to understand of all this. So we have here let's start with toluene. Let's say there was no toluene, right? The mole fraction was 0. So then its vapor pressure is 0. At the other extreme, if it's all toluene, well then that is the pure vapor pressure of toluene. which is something like 20, 30, 35 or so. Does it say above there? Page 431. Let's jump back here. No, it doesn't give the number directly, but you can read off. It looks to me like around 20. I'm doing it on the computer screen. Around 35. Okay. Now let's look at benzene. Benzene all by itself, and no toluene is over here in the top left, and it's like 97 or something, close to that. And then we're going to go down, and then the benzene has no vapor pressure if you don't have any benzene, right? If the mole fraction of benzene is 0. So what Raoult's law with regards to both the solids and the solvents being volatile, right? Volatile means they have vapor pressures, is the green line. You just add the two together, right? So you take the red line, add that portion to the blue line to get the green line. So that's my total vapor pressure. Okay, these kinds of graphs in physical chemistry, which is what this is, you're going to see lots of these graphs in your future chemical careers. You have to understand how they work. This is always a neat point where the this mole fraction, the vapor pressure of both of them are the same, right? Whatever that is, 0.7 for toluene, 0.3 for benzene, something like that. Those mole fractions, then you would add the two vapor pressures together. This region here added to the blue, and you end up getting the green. So you can look at these regions there. Okay. Let's try this one, this example here. Vapor pressure of a solution. We have a closed bottle which contains 5% acetone in water. We want to calculate the vapor pressure of this solution at 25 degrees Celsius. Now, acetone is what's used in nail polish remover, some industrial processes. You get a headache from that. People store it in the fridge so that they so that it doesn't evaporate too much. Acetone lately has been classified as a possible carcinogenic. So if you're using nail polish remover, you may opt for the non-acetone based nail polish removers. Okay, so helpful tips. We have, again, let's assume we have 100 grams of solution and we have 5 grams of acetone. So that means we have 95 grams of water. That's our little trick if you're given mass percents of things. So they very nicely give you the molar mass of acetone and the molar mass of water. So the moles of acetone is 5 grams over 58 grams per mole, 0.0862 moles. And for water, it is 95 grams over 18 grams per mole, or 5.28 moles. And then you can get the total. I like to always get the total. I don't like that they don't calculate the total, so I'm going to put it in here. 0.0862 plus 5.28, 5.3662. So that's my end total. And so then my mole fraction of water is 5.28 divided by 5.3362, which is 0.989. Okay, they got 0.985. 5.28 divided by 5.28 plus 0.0862, 0.984, good. So I'm just rounding off too much, aren't I? 5.28 plus 0.0862, 5.3. No, it wasn't that I was rounding off. It's that this 3 was supposed to be 6. So 5.3662. That's what it's supposed to be. So 5.28 out of 5.3662, 0.984. Very good. So that's the mole fraction of water, and the mole fraction of acetone is going to be 1 minus that, because the total has to equal 1. So the mole fraction of acetone, 1 minus 0.984, which is 0.016. Or I could just get the acetone molar mass 0.0862 divided by the total. If you want to like double check your work, always a good idea if you have the time, and you get 0.016. So now using the law where both components are volatile, the vapor pressure of the solution is the mole fraction of acetone 0.016 times its pure vapor pressure, which was given, or you look it up in a chart, plus mole fraction of water times its vapor pressure. So 0.016 times 30.7 plus 0.984 times 3.17, 3.61 kilopascals. So that is the vapor pressure of the solution. Let me scroll up for a second here. Oh, I've got the wrong button. And I want to see the temperature. Oh, 25 degrees. Okay, so that's happening at 25 degrees. Fine. Okay, let me go down a bit. And pure water is 3.17, acetone is 30.7, and it's somewhere between the two. The vapor pressure of the solution is intermediate between those of the solvent and solute, which is expected. It's closer to that of water because the mole fraction of water is much larger than acetone. And the practice exercise 9.7, I'm going to let you try that on your own. If you're stuck, we can go over it on the big whiteboard in Mr. Stevenson's class. Okay. The solution that we looked at is said to be ideal, and there are cases where you don't look at ideal cases, and so that's interesting. The distillation concept is not one that we talk about, or azeotropes in the class, so I'm going to omit that, and I'm going to jump to the boiling point and freezing point. Again, last day of class, if there's anything, last week of class, if there's anything that someone gets popped in that I said, oh, I said it'll be omitted, but it's not, we will go over it, okay? But azeotropes, this is not a topic that we talk about, or distillation, fractional distillation. Is it interesting? Of course. Can we talk about everything in this course? Of course not. So let's go to boiling point and freezing point. Remember, the normal boiling point is at 1 atmosphere. That's called TB, and the normal freezing point is also at 1 atmosphere. The normal boiling point of water is 100 degrees Celsius. The normal freezing point of water is also, sorry, it's not also 100 degrees Celsius. It is 0 degrees Celsius. So I mentioned how that boiling points are elevated and freezing points are depressed. So let's jump through this rather long discussion and get straight to the heart of the matter. So here we go. The freezing point depression is given by this equation. Delta TF equals I KF times B. So what is all this stuff? I is known as the Van't Hoff factor. And most of the time we're going to talk about the theoretical Van't Hoff factor. And what it is the number of moles of ions released into solution when a solute dissolves into that solution. That's the theoretical Van't Hoff factor, and that's the one we'll use almost all the time. There's variations we can talk about later, but we see here sodium chloride solid, equation of solubility, we did that in grade 12. You get Na plus aqueous plus Cl minus aqueous, so you get 2. So you say your Van't Hoff factor is 2. If I did something like aluminum chloride, AlCl3 solid, goes to Al3 plus aqueous plus 3 Cl minus aqueous, the Van't Hoff factor is 4. We've got 1 cation and 3 anions. If I have a calcium chloride solid, goes to Ca2 plus aqueous plus 2 Cl minus aqueous, the Van't Hoff Van Hoff. The Van Hoff. Sounds like a James Bond villain. I will get you, Bond. No, you won't, Professor Van Hoff. The value I equals 3. Okay, so I's, theoretical I's are going to be either 2, 3, 4. Could you have 5? Yeah, I guess you could have 5. You could have bismuth, Bi2S3, bismuth sulfide. You'd get 2 Bi, 3 plus aqueous, plus 3S, 2 minus aqueous, and your I would equal 5. So you see that your freezing point is going to be depressed more the more ions are being dancing around in the solution, right? The higher the I value is, the more the freezing point will be depressed. And again, it's because the not again, but it's because the solvents, they can't see each other as much. There's all this solid blocking their way to see other solvents to form their intermolecular forces of attraction and start freezing, start solidifying. So there's this interruption because there's all these solids in there. B is another way to talk about molality. This book uses B. Some other books do too. I like to write out the word molality, moles of solute per kilograms of solvent. We've looked at that in our previous lectures. And molality getting larger means you have more moles of the solute dissolved, which means more ions, which means a lower freezing point. So we have a direct proportion then. What the heck is this KF? That is, what is that now? That is the constant associated with the solvent or the solute? The solvent, right? It's a property of the solvent. Each solvent has its own freezing point depression constant, and has to do with the forces of attraction between those molecules. So that's the equation, and typically that will be given to you on the exam. You don't have to memorize that one. And the boiling point elevation, delta TB, is I KB times B, where B is the little b stands for boiling, the italicized B stands for molality. So it would be the boiling point elevation, so it would be TB of the solution minus TB of the pure solvent. Okay, because it's elevated. For the freezing point depression, I find this a bit annoying, but they flip it around and they say that that's TF of the pure solvent minus TF of the solution. Okay. So those are our equations. Okay, and they both result from a decrease in solution vapor pressure compared to the solvent. Here's a nice graph showing how all this works. We have a pressure temperature graph. This is actually a phase diagram. Let's see, you've already talked about phase diagrams. Yeah, you have in the last chapter. So, you know, triple points, things like that. So we have here, which one is which? This is our phase diagram for pure water. And then for the solution, you see, let's see, what's going on here? Which one is which? How the phase boundaries change when a non-volatile solute dissolves in the liquids, for example, salt in water. Okay, so, sorry, the solution is this one. This is the solution. This is the pure. Okay, so you see that the freezing point is decreased when I create the solution, and it is increased for the boiling point. And here we see the vapor pressure is lowered at some given point. 1.01 bar is 1 atmosphere, right? So that's our normal boiling point, normal freezing point. So we see that the boiling point is elevated when we have a solution, and the freezing point is depressed when we have a solution. Water, the KF value, you don't have to memorize it, you'd be giving it 1.858 degrees Celsius per times kilogram per mole, or degrees Celsius per molal is another way to say it, degrees Celsius per molal. I like to say it like that. And KB is 0.512. Okay, so let's try an example of this. Okay, maybe some of you have changed the antifreeze in the radiator of your Toyota Yaris or other superstar car that you may have. We have ethylene glycol. It's added to automobile radiators to prevent cooling water from freezing. Estimate the freezing point of a coolant that contains 2 kilograms. What page am I on? 435. 2 kilograms of ethylene glycol and 5 liters of water. Is this a high enough concentration to protect a radiator in Montreal? Oh, so you know this is a Canadian textbook, right? Because they said Montreal, where the temperature may be as low as -40. My goodness. Montreal -40? I think we're going to do this, guys. I think we're going to write Winnipeg, right? That's Montreal -40. Which is also -40 Fahrenheit, by the way. That's the bilingual version of it. So I am going to talk about freezing point lowering. So my KF I'm going to need. I need my KF, right? Got that. My I. Now, little pro tip. If you've got an organic molecule, like ethylene glycol, it's organic alcohol, the I is going to be 1. Okay, for organic stuff. Its I is 2, 3, 4, 5 if we're talking about ionic solutes. But if it's organic, so molecular solutes dissolved in solvents, your I equals 1, because the molecule ethylene glycol doesn't form a cation and an anion when it dissolves in water. It just gets surrounded by water in what's called a hydration sphere. Okay, so I is 1. We got the KF. Now we got to get the molality. Molality is going to be the moles of solute over the kilograms of solvent. Okay, so the moles of solute, well, it's 2,000 grams over the molar mass of ethylene glycol, which is 62.07. And you're going to get 32.22 moles. Okay, so that's the top. Kilogram of solvent, 5 liters of water. 5 liters. Each liter is a kilogram, right? It's 1 gram per mil. So if I multiply by 1,000, I get 1,000 grams in 1,000 mil. 1,000 mil is a liter. 1,000 grams is a kilogram. So 5 liters is 5 kilograms. Okay, so 32 over 5. It's a bit more than 6, right? That's a big molality, but that's what it is. 6.44. Okay. And then you just plug all those numbers into the, well, there it all is for you. The delta TF. So it is 12 degrees Celsius. So we can lower the freezing point by 12 degrees. So if we're driving around at negative 10 degrees Celsius in downtown Winnipeg or Montreal, everything's fine. But if we are driving around in minus 40, our whole cooling system is going to get screwed up because it's going to freeze. Obviously, this is not a high enough concentration to protect the radiator on a cold day in Montreal or in Winnipeg. So if you read the label on a radiator antifreeze, you'll see that to protect your car engine in a Canadian winter requires a 50-50 mix, right? This wasn't 50-50 mix. This was a lot less. So you'd have to put in more ethylene glycol the colder that it is. Okay? So now let's try one ourselves, just to become experts on it. All right, after 2 examples, you're an expert. Calculate the boiling point of an 8% by mass aqueous solution of sodium sulfate. Remember that this is an ionic solute. Okay, so Na2SO4, 2Na plus SO4. Excuse me. Don't worry, I was wearing my mask. 2Na plus SO4, 2 minus. So my I is going to equal 3. Boy, if I'm using the screencast 5 years from now, people are going to be saying, what the heck are you talking about? I equals 3. And so delta TF equals I. So 3 times 1.858. And then I got to get the molality. So let's get the molar mass of Na2SO4. I'll just go to the my good friend, the periodic table. Sodium, you think I can do that off the top of my head? No, I know some of you are probably going to Google this, but I'm not. Sodium is 20, Na2SO4, right? 22.99, 23. So 2 times 23 plus 4 times 16 plus 32. Sulfate's 32, right? Yeah. 142. Okay, so 142 grams per mole is the molar mass of sodium sulfate. So if I got 8% by mass, let's say I had 100 grams of solution, I'd have 8 grams of Na2SO4 and 92 grams of H2O. So my molality B would be 8 out of 142, that's the moles of solute, kilograms of solvent. Well, I got 92 grams of solvent, so divide by 1,000 to get kilograms. So that's the little tricks you do with when you have mass percents. 8 divided by 142, and all that divided by 0.092, 0.61 molal, or 0.612, fine. So that times 3 times 1.858 is 3.41. Holy smokes. Huh. Who noticed something here? I got what would be freezing point depression, right? Well, 3.41. So that we say, therefore, T final of the solution, we'll assume it's aqueous. We won't assume it tells aqueous, it will be minus 3.41. But look at the question. It didn't ask for freezing point. It asked for the boiling point. That's okay. It's all good. I actually did this on purpose. Delta TB is 3. That's my I. Now the KB for water isn't 1.858. That was the freezing point one. For water, it is 0.512. So 3 times 0.512 times the molality 0.612. Okay, so I did this all on purpose so you could see how it works. 3 times 0.512 times 0.612 0.94 degrees Celsius. So my final boiling point, well, if it's water itself, it's 100, but now it's elevated, so it's 100.94 degrees Celsius. Let's see if that is correct. What is this? Example 9, practice exercise 9.8. 100.94. Yeah, it's good. It's good. Now, you may ask, which one experimentally is done more often, the freezing point depression or the boiling point elevation? And the answer is freezing point depression. The reason being, because in aqueous solutions, okay, your Kb is much smaller than your Kf. The differences are harder experimentally to differentiate for boiling point elevations than freezing points. So when there's smaller differences, experimental error gets more important. So if you have your choice when designing an experiment to get information, you want to do calculations of the lowering of the freezing point rather than the elevation of the boiling point. Okay, I'm going to leave osmosis for a second because we don't always get to that in the class. And we're going to do that. I want to tell you that 9.5 colloids we never get to, so don't worry about that. That's omitted. So all the stuff in 9.5 and onward in the chapter are not discussed, which is the way that is. So really the big chunks in this chapter are 9.1, just to get the natured solutions and those equations. 9.2 a little bit, yeah. 9.3 not much. We don't really get into Henry's law. 9.4 is a big one. Colligative properties. And 9.5 we omit. Now, before I again go to osmosis, I want to do another one about boiling point depression or boiling point elevation or freezing point depression. So let's see here. I wonder if we can find one here that I want to look at. Oh, let's look at this one here. Here's a good one. 9.42. Okay, so this is the end of chapter stuff. This one I have seen on tests. I actually saw this one. I used to teach sometimes in the evenings and in the summers an MCAT prep course. MCAT is the medical college admission test. That was for one of these companies that you pay big money to, and they don't pay me much. I won't say the company, that wouldn't be fair. No, I won't say it. But it's a program that helps you do well on the MCAT, like it's a test prep program. So this kind of question in the physical chemistry always seem to appear. So list the following aqueous solutions in order of decreasing freezing point and explain your listing. Okay, so again, aqueous is a big word here, right? So we know that delta TF equals IKF times B. So let's get the I's for them. For sodium chloride, I is 2. For NH3, I is 1. For MgCl2, it's 3. And for NH3, it's 1. Now, the moles, we're going to have let's all assume we have the a kilogram of solvent. Okay, so the solvent's the same. 0.3 moles. I mean, well, okay, we got moles per liter. Think of a liter as pretty close to a kilogram. So we got 0.3 moles of NaCl, but there are That means 0.3 moles of sodium plus and 0.3 moles of Cl minus. So it's really together it's 0.6, right? NH3, well, there's just one of those, but that's swimming around at 0.75, so that's going to be more effective at lowering the freezing point. MgCl2, where there's 3, H at 0.25, so that's 0.75. So that's going to be about as effective as NH3. And then a less concentrated NH3 would be 0.25. So decreasing the freezing point. So the one that will decrease it the less will be this guy, right? Because you only have 0.25 moles of NH3 thrown into the solution, into the aqueous solution. Then would come the NaCl, because there'd be 0.6 moles in total of cation and anion added together. And then it would be a tie between these two, right? The NH3 and the MgCl2. Now, if someone really was forcing you to make a decision, and I don't have the answer key for this one handy, but if they were really forcing you to, remind me, we can look at it in class if we have time, I would have to say the MgCl2 would be the next, because this I value is a theoretical value. In reality, it would be slightly less than 3 because you get what's called ion pairing forming. It'll be slightly less than 3, and then NH3 would be the next one. But that's the way that one would work. Okay, let's go up here. Well, 9.43. Now that one we do have an answer to, so let's go to the end. Now this will be the end of the book, right? Answers to practice exercise. So we're going to go to 9.43. This is where you're going to zoom up the speed of the YouTube, right? 9. Okay, so this one we got answers for. Let's see how this works. List the following aqueous solutions in order of increasing boiling point and explain your listing. Okay, so again, aqueous solution. So NaCl, I is 2, so that'll be 0.4 altogether. Sucrose, I is 1, so that'll be 0.2. Magnesium chloride, theoretically, about 3 times 0.25 is 0.75. And then we got sucrose, which is organic, 0.4. So the lowest amount would be 0.2 molar sucrose. So that's going to increase the boiling point the least of them. So it'll be 0.2 molar sucrose. Then a tie between sodium chloride and the 0.4 molar sucrose, and then the magnesium chloride. What do we got here? 0.2 molar sucrose. Then they say the 0.2 molar NaCl. Then the MgCl2. Sorry, no. Let me do it again. 0.2 molar sucrose, then they go NaCl and the 0.4 molar sucrose, and then the MgCl2. And again, this one is being a little nasty because you might say, oh, it should be a tie between the sucrose, between the 0.4 molar sucrose and the 0.2 molar NaCl. But the theoretical I is just that, theoretical. In practice, it would be a little bit less than that. Okay. The osmotic pressure I'll get to in a second. I want to see if there's one other style of question here. Not all of it. Yeah, this one here. Here's a good one. This one I like to do a lot. 9.59. Compute the molar mass of vitamin C. Huh, they don't give the answer to that one. Okay, we'll Google it after. Molar mass of vitamin C. If a solution contains 22 grams in 100 grams of water, so that's 0.1 kilograms, right? We're going to need molality. So 22 grams over the molar mass divided by whatever the molar mass is. That's what we got to solve for. All divided by 0.1 equals the molality of the solution. The freezing point depression is 2.33, right? So 2.33 is I. Now I equals 1 because we're talking about an organic molecule. Kf is, I forget, 1 point. I don't have the answer, so let me go back here. 1.86 or 1.858? The 1.858. Right, so 1 times I is 1. 1.858 is my value for water's freezing point depression constant, then times the molality. So I can get the molality from this equation. So it's 2.33 divided by 1.858. 2.33 divided by 1.858, and I get 1.254. So B equals 1.254. So multiply that by 0.1, and I get 22 over the molar mass equals 0.1254. So then the molar mass is 22 divided by that. Oh, I shut up the whole thing. 22 divided by 0.1254, and I get 175.4. 175.4. So I don't have the answer key, but I'm just going to Google that, get the molar mass of vitamin C, and see how close we are. What is it? Why is it go to Bing? I don't like Bing. 172. What did we get? 175. Okay, so there is some experimental error with that. That's good enough. So that's a good question, and 9.58. That isn't as fancy. I wanted to just show you that you can use freezing point depression data to determine molar masses, as you see in 9.59. Oh, my dogs are making some noise. Let's see if I should do another one associated with that, or should I do the osmotic pressure? I'm stalling a bit on the osmotic pressure because we don't always get to it in the course. Okay, let's see. Advanced problems. Those look too scary. Okay, so let's go back and look at this last topic. Why not? Here we go. Jump back a few pages. Osmotic pressure is given by the capital Greek letter pi. It is used in biochemistry when you're talking about blood cells and blood transfusions. You don't want to have the blood cell, especially red blood cells, rupture, so you have to put in the proper concentrations in an IV bag, for instance, or else you get into trouble. So you might have seen the movie Osmosis Jones. I think the biology teachers always show that movie around holiday time. Anyways, osmosis is pressure differences arising from different sized molecules moving through a semi-permeable membrane, which you got these little holes and you got these molecules moving back and forth between them. You maybe do this in biology. I'm not sure anymore what's going on there, but it's all good stuff. So you have different sized molecules. The solvent molecules might not be able to go through from one side to the next. The solid particles might. So it's just a biochemical process. We just want to get to the equation. How does it help us get some information? So here's the equation. 9.7. The osmotic pressure is the concentration in molarity times the gas constant times the temperature in units of Kelvin. And so if you're ever asked to calculate osmotic pressure, it is CRT, where the gas constant is 8.314 liters kilopascals per mole per Kelvin. Ocean water, you can get it. Ocean water is obviously a solution. If you take a look at all salts, some data shows you can have, let's say, 1.13 moles per liter of some dissolved salts in an ocean, and then multiply that by the gas constant, and then, because it is a pressure above, right? So then times the temperature. You see kelvins cancel, moles cancel, liters cancel, so you get kilopascals. So it means if you had pure water and ocean water on opposite sides of a semi-permeable membrane, an external pressure of 2,800 kilopascals would have to be applied to the ocean water side to prevent osmosis. Reverse osmosis, by the way, has been used to desalinate water. That means get rid of the salt to make it into drinking water, so it is an important process. That's the equation. Let's do an example of it here. Isotonic intravenous solutions contain 49 grams per liter of glucose. What's the osmotic pressure of blood? Okay, so 49 grams per liter. So we want to get that into moles per liter. So you got 49 grams. The molar mass of glucose, you look it up, or it's given in the question, 180 grams per mole in 1 liter, so 0.272 moles per liter. Temperature, we're assuming the person is hot-blooded, so 37 Celsius or 310 Kelvin. So you get 0.272 moles per liter times the gas constant, 8.314 times 310 Kelvin. So you get 701 kilopascals is the osmotic pressure. Okay. Osmotic pressure, by the way, is the one colligative property whose magnitude depends on molarity, not on molality. Okay, and you can try that practice example if you want. And now here's where it's used to get molar masses. I know I did one with freezing point to get molar masses, but often osmotic pressure measurements are used to get molar masses, especially for large molecules. So the molar mass can be determined from this equation using this data. So let's try to prove it for a second. So let's see. Pi is CRT, we know that. And C is moles per liter, right? So that'll be pi. It's not the Greek, it's not the 3.14, but pi. Oh, I seem to have lost my pen here. Draw. Okay, well, I'm not going to stop the lecture because I lost my pen. That's strange. Okay, this. Okay, anyways, you can, I'll do it in class, okay? So moles per liter, and mole is grams over molar mass. So you plug those in and you get the molarity, and then from there, oh, I'm back. Okay. You knew I wasn't going to give up that easily, right? So C is moles per liter. So pi is C times moles, which is N over V RT. But N is M over capital M. So C little m RT over V capital M. The C went away. C is N over V. So it's MRT over VM. And I think you're given that one on an exam. If not, you memorize it. So you isolate for molar mass, little mRT over pi V. So let's use the equation here. We got a 25 mil aqueous solution, so 0.025 liters. We got 0.42 grams of hemoglobin, which is in your, it's an iron molecule in your blood, right? Transferring oxygen all over the place. Gives you the osmotic pressure in kilopascals, gives you the temperature, what's the molar mass? So you're just going to plug everything in. So you got the mass of the solid is 0.42, R is 8.314, temperature is 300. The volume of the solution is 0.025 liters. Plug it in, and look at that large number you get. 6.8 by 10 to the 4th grams per mole. Okay. You can try practice exercise 9.1 on your own. Okay, I think that's good. Let's see if I can save this.